In the previous lecture, we derived a formula for approximating the solutions of a function called Newton's method. And we did that using a very graphical, geometric, algebraic method. Now, I like to start with that approach. I think it's very visual and really helps to give students an understanding of how the method works. It's not, however, the most useful approach from a mathematical perspective. So in this lecture, we're going to derive the formula again, this time using a more calculus-based approach using the Taylor series. And that's also going to give us the background details that we'll use in a later lecture to come up with a bound on the error and to see how quickly the method converges. All right, so first let's get the details out of the way. We're going to start with the C2 function, that is a function whose first and second derivatives are both continuous on a closed interval. We'll let P be a value on that interval where such that f of p equals 0. That's the exact solution. We'll let p sub 0 be an approximation of that number. And we have that same additional requirement here that the derivative cannot be 0 at that approximation. Now, I've also got one extra little requirement here at the end, that the absolute value of p minus p0 is small. And what that's saying is our first approximation needs to already be reasonably good. All right, so with all that out of the way, right, let's take a look at the Taylor series of this function. And I'm going to expand that around our approximation P0. Now, the next thing I'm going to do, I'm going to evaluate this function at P. So every x gets replaced with a P. From here, remember that P is the actual root. So f of P over on the left-hand side is equal to 0. And this p minus p0 squared part in the far right-hand term, if p minus p0 is small, then the square of that is really small, right? Smaller still. So small enough that it's going to be approximately equal to 0. That's why I substituted 0 in here and I changed the equals to approximately equals. So now I'm just going to rewrite that equation, right? Taking off that last term that's equal to 0. And finally, I'm going to take this and I'm going to solve it for p. I'm going to solve it for the exact solution. So the exact solution is approximately equal to p0 minus f of p0 over f prime of p0. And that is what I'm going to set equal to p1. Right? That is our next approximation. Right? So that's how to get from the first approximation to the second. If we generalize this, we get this formula here that tells us how to get the next term in the sequence from the current term in the sequence. Same formula we came up with before, right? Exact same thing. And again, just in case you didn't watch that lecture, you notice that on this step you can see why we have that requirement that the derivative can't be 0 at the approximation value, because that's the term here in the denominator. Right? If it were 0, the denominator would be 0 and the whole thing would stop working. So one thing I want to emphasize about this method before we move on is that this is just another example of the iterative methods we discussed previously. If you remember those discussions, the first thing we always had to do was come up with a function that we could iterate that had a fixed point where the original function had a root. All we've done here is come up with a function, g of x, that we can iterate to generate a sequence that converges to the required root. And that's why I've written this on the second line, right? Where I put xn in there in the formula for x, and xn plus 1 is the function value. That's our next approximation. So we are going to show the correctness of this, right? At this point, hopefully it's not at all obvious why this sequence has to converge, much less converge to the root. So we are going to talk about that. We're also going to talk about the method's convergence level. But before we do that, I want to take a look at some specific examples of how the method can be used to find the roots of specific functions, so you can kind of see what it looks like in